Alright, hello class. In this video we're going to be talking about conservative vector fields. And this is what we were looking at at the end of the last video, where we found one of our vector fields. It didn't seem to matter what path we took, we would get the same circulation each time. And then the other vector field, it did matter which path we took. Okay, so what it comes down to is that if a vector field is conservative, then it's not going to matter what path you take from, say, point A to point B. The circulation will always be the same. Okay, so let's talk a little bit about what we mean by conservative vector field. Okay, so a conservative vector field basically is a vector field that is the gradient of a function. It's a gradient field. Okay, so as for the official definition, a vector field capital F, which we'll say is little f comma little g, is conservative if, and it's really an if and only if, it is the gradient of a potential function, which we use phi of xy. What does that mean? Well, that means capital F is conservative if there exists a phi of xy such that the gradient of phi is equal to capital F. Right? And this is the same thing as saying that, well, the gradient of phi, if you remember, that's phi sub x comma phi sub y. So if this is equal to little f little g. In other words, phi sub x is equal to little f, and phi sub y is equal to little g. So in other words, f conservative basically means that f is a gradient of some function. Okay? In other words, there's some phi such that if we take the gradient of phi, we'll get to our vector field. Okay, so here's an example we've talked about previously. We've sort of seen as an example, but notice or remember, right, that this vector field, which is 2x comma 2y, is the gradient of this function here. Phi sub xy is equal to x squared plus y squared. Right? Because the gradient of phi, right, that'll be phi sub x comma phi sub y. Well, that's going to be the x derivative of phi, so that will be 2x, and then comma the y derivative of phi, which will be 2y, and that is our capital F. Okay, so capital F is conservative. Alright, so this is all well and good in an example like this, that we say start with the original function and take the gradient. The important distinction is, how do we test that a field is conservative without knowing what the gradient is? Alright, so that's really what we're going to talk about here. Because, alright, if you start with the function and then take the gradient, of course, that field that you end up with is going to be conservative. But how do we test it the other way around? Okay, so to just have it written out here, how do we test whether a vector field is conservative without knowing what the potential function is? And we're going to talk about the method of how we find the potential function, but we want to be able to test that a field is conservative before we start trying to find what the potential function is, right? We don't want to waste our time if the field isn't even conservative. Okay, so it's actually a neat little test. What we do is that if capital F is, say, little f comma little g, we test whether f sub y is equal to g sub x. And so basically, if f sub y is equal to g sub x, then capital F is conservative. Okay, and on the other hand, of course, if f sub y doesn't equal g sub x, then f is not conservative. So what are we actually checking here? Okay, well, what we're actually checking is whether this field here represents, say, a nice original function, because if capital F is conservative, okay, then as we've talked about, there's a phi where the gradient of phi is equal to f, right? And we've talked about this before. This means that phi sub x comma phi sub y is equal to little f little g, and phi sub x equals f, and phi sub y equals g. So if f is conservative, we have this. Now, when we test here the f sub y and g sub x, what we're doing is we're starting here, okay, and let me rewrite this step again. Okay, we're starting here, and then if I have that phi sub x is equal to f, I take the y derivative of both sides. And here, if I have that phi sub y is equal to g, I take the x derivative of both sides. And the reason that we're doing this is because this tells us that phi sub xy is equal to f sub y, and phi sub yx is equal to g sub x. And remember what we know about the mixed partial derivatives, that if phi is twice differentiable and all that fun stuff, these mixed partials should be the same. Okay, so if phi is a nice function that's differentiable, then phi sub xy must equal phi sub yx. I believe this was Clairaut's theorem, right? So from Clairaut's theorem, these two must be equal, meaning f sub y must equal g sub x, right? So this is basically checking whether the mixed partials will match. Okay. So yes, essentially, do the mixed partials of this phi, will they match? If they don't match, then no phi will exist. If they do match, then a phi does exist. Okay, so that's what this check is doing. It's checking to make sure the mixed partials match. Okay, so this is for a two-dimensional vector field. I'll mention we can also do this for three-dimensional vector fields, which I haven't mentioned much in this particular module. All the things we've been doing can still be done with three-dimensional fields. I just find it a little more difficult to visualize and talk about. But all the math so far will hold the same. This is pretty much the first instance that we will come across where that isn't true, where things will be slightly a little more work with a three-dimensional field. Okay, but let's take a look at some vector fields and see what we can see. Okay, let's determine if the following vector fields are conservative. All right, so for capital F, if it equals x squared minus yx, comma y squared minus xy, well, this guy here is our little f, and this guy here is our little g. So we're going to do f sub y. So remember, you're always doing the opposite derivative of what component you're in. So since we're in the x component, we're going to take the y derivative. So the y derivative of f, well, the x squared part will go to 0, and the minus yx will become just a negative x. All right, so we get negative x. Okay, then g sub x, well, once again, the y squared part is 0, and the minus xy, well, the derivative of x with respect to, the derivative of negative xy with respect to x is going to be negative y. Well, these do not match. F sub y does not equal g sub x, so f is not conservative. Okay, how about this second vector field? Xy minus 1/2 y squared plus 3x squared, comma, 1/2 x squared minus yx plus y cubed. So let's see what we have here. Once again, do this one in a different color. This will be our little f. This will be our little g. And f sub y. So we'll take this derivative with respect to y. So we'll get x, all right, minus 1/2 y squared. That will give us y. And then the plus 3x squared disappears. That becomes a plus 0. So we get x minus y. Okay. Then g sub x, well, taking the x derivative of g, we'll get x. The derivative of minus yx with respect to x will be minus y. And then we will get plus y cubed, so 0, since we're taking the derivative with respect to x, so we get x minus y. And in this case, these are equal. Okay, so f sub y equals g sub x, so this f is conservative. Okay, just to give you a look and to show that it can be kind of tough to tell conservativeness just from looking at a vector field, here's the first one that we looked at that was not conservative. Okay, and here is the second one that is conservative. So you can kind of see how, I mean, yes, both kind of look like they're balanced. However, as I was just saying, it's kind of hard to tell just from the graph which one would be conservative and which one wouldn't be. Now, sometimes it will be completely obvious, and sometimes it won't be. So we'll have a better idea of how we can analyze this as we go further. Okay, a lot of this has to do with what the curl is, and of course we haven't talked about that yet, but once we get to that, that will be another way to distinguish from a graph what's happening. Okay, so I just wanted to show what those looked like before we went any further. Okay, let's do one more example of a two-dimensional field here. Say we have the field 2x e to the xy plus x squared y e to the xy, comma x cubed e to the xy plus 2y. Okay, so we'll do it in green this time. Here's our little f, here's our little g, and so f sub y. Well, when we do f sub y, keep in mind that this 2x now is just a constant, so it's just going to be now the derivative of e to the stuff, which will be itself, then times the derivative of the stuff, but since it's the derivative with respect to y, it will be an x here. Okay. Then, when we do this piece, the x squared can just come along for the ride, but I have a y e to the xy. So this is actually going to be a product rule. So it'll be x squared times 1 times e to the xy left alone, then plus x squared y, then times the derivative of e to the xy, which will be the same e to the xy times the x. Okay, so we can actually, I suggest we simplify this somewhat. I'm going to take out the e to the xy, and we'll get 2x squared plus x squared plus x squared y. Okay, so actually it looks like we can take out an x squared while we're at it. So we'll have x squared e to the xy times, it looks like it'll be, what, a 3 plus y? Okay. Then we'll do g sub x. Well, g sub x, for this first piece, that's going to be a product rule, right? So it will be 3x squared times e to the xy left alone plus x cubed, now times the derivative of e to the xy, so that will be e to the xy. Now we're taking the derivative with respect to x, so times the derivative of the stuff this time will be y. And then we have 2y here, which just goes away. Okay, so we have, when this simplifies, it looks like, again, we could take an x squared out. Okay, so we'll get x squared e to the xy, and we'll be left with a 3 plus xy. And I realized here, sorry about that, I missed an x here. This should have been x cubed, right, in this third piece. Sorry about that. So that should be an xy here. And there we go. My g sub x becomes an x squared e to the xy, 3 plus xy. So these are the same. Therefore, this field is conservative. Okay, for 3D vector fields, we do pretty much exactly the same. We just have more things to check, right? Because if capital F is equal to little f, little g, and little h, then that means we have a gradient in terms of phi sub x, phi sub y, and phi sub z. So we need to check that all partial or second partial derivatives match. Okay, so we need to show that phi sub xy is equal to phi sub yx. We need to check that phi sub, let's say, xz is equal to phi sub zx. And we need to check that phi sub yz is equal to phi sub zy. So now we have 3 things to check. It's the same idea. We just need to make sure all 3 hold. And remember, if we're saying that these are equal, that means phi sub x is equal to f, phi sub y is equal to g, and phi sub z is equal to h. So here what we're basically saying is, well, phi sub x is f, and phi sub y is g. So we have the same thing here. The f sub y is equal to g sub x. Here, the phi sub x is f. So we need to check that f sub z is equal to, well, phi sub z is h. So we need to check that f sub z is equal to h sub x. And finally here, phi sub y is g, and phi sub z is h. So we need to check that phi sub y is g. So we need to check that g sub z is equal to h sub y. Now here's how I remember, here's how I keep this straight. I have a little table that I do. Okay, so I make myself a little table. And okay, well, instead of a table, I make a 3x3 grid, right? And say on the top, I put F, G, and H, and along the side, I put, say, the derivative with respect to X, the derivative with respect to Y, and the derivative with respect to Z. And then I put these together. So here, this would be F sub X, G sub X, and H sub X. Here would be F sub Y, G sub Y, and H sub Y, and then this would be F sub Z, G sub Z, and H sub Z. Okay, now what I do is I completely mark out this diagonal, right? So we don't need to check any of these, right? You'll notice that the F sub X, G sub Y, and H sub Z, we don't use any of those in our check. And then now that I have this, we're just checking to make sure that the guys opposite of the diagonal are equal, right? F sub Y, G sub X, F sub Z, H sub X, G sub X, H sub Y. All right, I find this a nice way to check this. Okay, is just ignore the diagonal and make sure the opposite diagonals match. Okay, so to show you an example of this, let's say we have the vector field capital F. It's the field 2xy minus z squared, comma x squared plus 2z, comma 2y minus 2xz. All right, so here will be our F, our G, and our H. Okay, so I'm going to make my little grid here. I don't know how much space I'll need, but I'll put, say, F, G, H, and my derivative, derivative, derivative. Okay, give myself a little more room. I'm not going to worry about the diagonal, of course, right? F sub X would go here, but we don't really care about that. So what we're going to do instead is next, let me make this in green, G sub X. Well, G sub X will be 2x plus 0. Okay, then H sub X, let me do that in blue. H sub X, well, the 2y will go to 0, and the 2x will just go to 2. So it will be 0 minus 2z. Okay, now I'll do the y column. So I'll do F sub y. Well, F sub y I'll do in green. So F sub y, 2xy, that will become 2x, and the minus z squared will become 0. Okay, so look at that. These two match. G sub y, we don't really need to worry about. We don't check that. And then H sub y, I will do that. Let's do that in pink. So H sub y will be 2 minus 0. All right. Then now we'll do F sub z. So F sub z, this whole first part will go to 0, and then we'll have minus 2z. So we see here that these two match. Okay. For the next piece, the G sub z, we'll do that in pink. G sub z, the x squared will go to 0, and the plus 2z will become plus 2, and we can see that these match. And then, of course, the h of z we don't need to bother with. So all the things that need to match, match. So F is conservative. All right, let's take a look at another example. Let's take a look at this field, z minus y, comma z plus x, plus z squared plus y squared plus x squared. So we want to check that this field is conservative. So let's set up our little grid here. I'll do my f, g, h, and then we'll do our derivatives. Derivative with respect to x, y, and z. Okay. Not sure how much room I'll need, but hopefully this will do it. All right, so let's start going through. F sub x, we don't need to check. Now, g sub x. G sub x, let's match the colors here. G sub x will be 1, right? And just to stay consistent, it'll be 0 plus 1. And then h sub x will be 2x. So it'll be 0 plus 0 plus 2x. All right, so just trying to match the colors here. All right, now g sub y, or sorry, excuse me, f sub y. F sub y will be -1, so I'll be consistent here. 0 minus 1, and check this out. These two do not match. We're done. F is not conservative. Okay, so we don't have to go any further here. F is not conservative. So thankfully, the second you see one that doesn't match, you're done. Okay, so now that we know how to check whether a function or whether a vector field is conservative or not, well, if a vector field is conservative, that means a potential function exists. So how do we find phi? Okay. Well, so basically, if capital F, which is little f comma little g, let's say, is conservative, then gradient phi is equal to f, which is basically telling us that phi sub x is equal to little f, and phi sub y is equal to little g. So to get from here to finding what phi is, we're going to use integration. Okay, and it's kind of hard to write in general terms, but we're going to choose one. Say we choose the phi sub x. Okay, we're going to integrate phi sub x with respect to x. Okay, which is going to give us a candidate for phi. Okay, and then this will say maybe be capital. I can't use capital F, can I? This is going to give us some version of phi from here, right? We're going to get, let's call it f bar plus, and I'll explain this in a bit, but plus some constant with respect to y, and then from here we're going to differentiate this with respect to y again, because whatever this is differentiated with respect to y is going to equal g, and then we can integrate again. Okay, so this is sort of the idea. We go from f sub x, use integration, then use the opposite differentiation to get back to the other one, and then we're going to use another integral to solve for the final phi sub xy. Okay? Like I said, trying to write this in general terms is not very nice. It doesn't work very well. So here's what we're going to do instead. Let's just look at an example, and I'll explain what we're doing step by step. Okay, so let's go back to one of the vector fields we've already looked at. Say xy minus 1/2 y squared plus 3x squared, comma 1/2 x squared minus xy plus y cubed. We've already shown or proven that this field is conservative. So let's go through and find the potential function. So this means there's a phi such that phi sub x is equal to xy minus 1/2 y squared plus 3x squared, okay? And phi sub y is equal to 1/2 x squared minus yx plus y cubed. Okay, sometimes it matters which one you want to start with, other times it doesn't. So if it doesn't really matter in this case, I'm going to start here. Okay, so if I have phi sub x is equal to this thing, I'm going to integrate both sides with respect to x. Okay, so we will get the integral of phi sub x dx is equal to the integral of xy minus 1/2 y squared plus 3x squared dx. And we're going to integrate these things. Well, this part's just going to become phi. Okay? This side, on the other hand, well, now we're going to integrate with respect to x. Now, here's the key. X is our variable here, but we treat y like a constant. Okay? And just wrote this here, and notice I'm making a big deal about we're treating y like a constant. See in a second why that is. Okay, so the integral of xy with respect to x, well again, y is the constant, so we get 1/2 x squared y. Okay. For this piece, this is just a constant now, this 1/2 y squared, so we'll just get minus 1/2 y squared x. And then the integral of 3x squared with respect to x will just be plus x cubed. Then we're going to put a plus c, but in this case, it's not just a constant, because it can be a constant or an arbitrary function of y. So this is our arbitrary function, or sorry, our arbitrary constant that we usually have, but remember, y is treated like a constant. So technically this is our arbitrary function of y. Right? Because we could have any y function here, and if we differentiated this with respect to x, any of our y's would go to 0. Okay? So this is the thing that makes this work. It's the thing that makes this thing tick, and it's really the thing that makes it complicated. Okay? So now that we've gotten here, we need to find this c of y. Right? So we need to find c of y. Okay? So here's what we're going to do. We're going to now differentiate this with respect to y. So I'm going to differentiate phi sub y, and I'm differentiating this with respect to y. All right, so here the y disappears and we get 1/2 x squared. Here the derivative of 1/2 y squared will simply be y, so we get minus yx. Then this whole piece here goes to 0, and then the derivative of some function of y, we're just going to write that as c prime of y. Now, what has this given us? Well, we're going to compare this to what we have up here. Right? So we're going to compare it to our g. So, in other words, 1/2 x squared minus yx plus c prime of y must equal, okay, 1/2 x squared minus yx plus y cubed. This came from our work. This is g. Okay, so this thing must match this thing. Well, notice that the 1/2 x squared is the same, the minus yx is the same, so this tells us that c prime of y is y cubed. And now we can solve for c by integrating, right? Because we will just take the integral, use another color here, the integral of c prime of y dy is equal to the integral of y cubed dy. Okay, so we will get c of y is equal to, this will be 1/4 y to the 4th, plus now some arbitrary constant d. Okay, so now that we have solved for the cy, we can put it back in. Right? So our final answer here is going to be phi of xy is going to be 1/2 x squared y minus 1/2 y squared x plus x cubed plus 1/4 y to the 4th plus some arbitrary constant d. Now, I will mention that some of the homework doesn't really ask you to put an arbitrary constant, but we can go ahead and do that. Okay. And then sometimes it will tell you what letter to use for your arbitrary constant. So just be aware of that when you're getting your final answer here. Okay. Now, that may seem like quite a bit of work, and so I'll go through another example here because it's kind of, it can be kind of hairy. But if I check this by taking the gradient, okay, well, phi sub x, that will be xy here, minus 1/2 y squared plus 3x squared. And then phi sub y will be 1/2 x squared minus yx plus y cubed, which, if we go back and check, that's our original f. Okay, so that aligns. All right, so the method in general, I always think of it as sort of like I almost think of it like a W, because what you're doing is, say you start with phi sub x and you integrate with respect to x to get a phi, right? And I'll call that a phi star. Then you take that phi star and you differentiate with the other variable, right, to get you back to the phi sub y and the g. And then you integrate again to get you back to the actual phi you're looking for. Okay, so it sort of makes a zigzag. So it's sort of a zigzag, but we don't have to start with a phi sub x. Okay, so for this particular example, right, we've already shown it's conservative. We don't have to do that again. So I want to show that we don't have to start with phi sub x or the f, right? Because this would be our little f, and this would be our little g. We can start with the function that will be the easiest to integrate. So if we look here, well, if we start here with f, if we integrate this with respect to x, note that we're going to have by parts and by parts, right? So I don't want to start there. I'd rather start here because integrating with respect to y, there's no by parts here. Okay, so that's where I want to start. All right, so phi sub x is equal to 2x e to the xy plus x squared y e to the xy. And phi sub y is x cubed e to the xy plus 2y. I want to start here. Because, again, there's not going to be any integration by parts required, whereas here it would actually be 2 integration by parts. Nasty. So let's integrate this with respect to y. So this example was really just to show that you don't have to start with phi sub x if you don't want to. Okay, so we're going to integrate phi sub y with respect to y, and x cubed e to the xy plus to y with respect to y. Okay, so we'll get phi is equal to, now again we're going to integrate with respect to y. So the x cubed is just a constant. E to the xy, well, its integral is itself divided by the derivative of the stuff in the exponent. So we're going to be dividing by x here, right? Specifically x times 1. Then here, 2y, its integral will be y squared. Okay, then plus an arbitrary function, and I'm going to start with d this time, just so we can end with c. This is going to be an arbitrary function of x. Because we're integrating with respect to y, that means x is the constant here. Okay? So if I want to make that look a little nicer, that tells me that phi is x squared e to the xy plus y squared plus d of x. Okay? Now, so we've integrated with respect to x. Now we're going to differentiate with respect to y. So I'm going to differentiate with respect to y to get that phi sub y, we integrated with respect to y. Now we're going to differentiate with respect to x. I apologize for that. Okay, so here, this is going to be a product rule. We'll get 2x e to the xy left alone plus x squared, then the derivative of e to the xy, which will be itself, times the derivative of the stuff, which will introduce a y, then plus d prime of x. All right. Then I'm going to take this and line it up with this. Okay, so I want that 2x e to the xy plus x squared y e to the xy, that's going to equal 2x e to the xy plus x squared, let me rewrite this as x squared y e to the xy plus d prime x. All right, so these cancel. And what are we left with? Well, we're left with the fact that d prime of x is equal to 0. Okay, so this step we differentiated with respect to x. Now we're going to integrate with respect to x. Or you can quickly just say, oh wait, if d prime is a 0, this means that, let me use a different color here. This means that d of x is simply a constant. Right? So you could go ahead and go through the integration if you want. But the integral of 0 will be a constant. Okay? So we can just take this d and replace it with a constant. This happens sometimes. Right? So our final phi sub xy will be x squared e to the xy plus y squared plus some arbitrary constant. Okay, so I want to show that we need to check whether a field is conservative before we try and do this. So if we tried to find phi with this field x squared minus y comma y squared plus x, so if we just try to find phi indiscriminately, no idea if I spelled that right, we can find ourselves in trouble. So without checking, if you just say, oh, well, f sub x is x squared minus y, and phi sub y is y squared plus x, and you just start going through your motions here, okay. Phi sub x dx, that will be the integral of x squared minus y dx, so we'll get 1/3 x cubed minus yx plus some arbitrary function of y. Okay, so there's our phi. And when we go to find our phi sub y, this will zero out. We'll get minus x plus d prime of y. Okay, and if we then try and compare it to this, well, what you'll find is something strange. We'll get negative x plus d prime of y is equal to, on this side, y squared plus x. And notice that these are not going to cancel, right? The minus x and the x don't cancel. In fact, what we have is, if we move that over, we have y squared plus 2x is equal to d prime y, but this can't be true, right? This cannot be true because this has to be a function of just y or constants. So this is already bad news, right? This is already a problem. However, suppose you didn't think it was, and you went ahead and integrated with respect to y. You'd still end up with some weirdness happening, because you'd get 1/3 y cubed plus 2xy plus c. And if you tried to put that back into here to make your phi, right, if you went ahead and made your phi equal 1/3 x cubed minus yx plus 1/3 y cubed plus 2xy, so that will make that a plus xy at the end, plus c, you're going to run into trouble when you then take the gradient, because you will get x squared plus y, comma, x plus y squared, and that is not what we started with at all. Right? That is not our f. Okay, so this whole thing here is garbage, and that's because f sub y is -1 while g sub x is 1. These don't match. F is not conservative. Okay, so phi does not exist. Okay, no phi exists such that its gradient is equal to capital F. Okay, so you have to check that the field is conservative. That's got to be your first step every single time. Okay, I'm going to put a cut in this video here and come back for a part 2 to finish talking about conservative vector fields and just how they can simplify our lives when we're trying to calculate circulations and